Hi, welcome to Office Hours. My name is Patrick Curran, and along with Dan Bauer, we make up curran-bauer Analytics. In this episode of Office Hours, I'm going to explore the basics of the structural equation model. This episode is an introduction to the SEM, and additional episodes explore more specific aspects of the model and how we might encounter it in practice. Briefly, the SEM is an umbrella term that captures a whole lot of models that we've been exposed to before in other classes, but then others are more advanced and interesting applications that we may not have considered before. So we'll find that the SEM actually encompasses the entire general linear model. So things you've already learned in terms of t-test, correlation, regression, analysis of variance, all of those classic techniques fall under the SEM, but then all of those can be expanded to path analysis, confirmatory factor analysis, the full structural equation model, which introduces path analysis with latent variables. It can expand into multiple groups analysis and longitudinal data analysis. And then we can even go a step further and encompass the generalized linear models through the use of what are called nonlinear link functions. So we can have binary outcomes that would be a logistic regression, or we can have count outcomes or ordinal outcomes or non-normally distributed outcomes. And so the SEM is a very broad set of methodologies that allow us to do things with our data in ways that are closer and more powerful tests of our research hypotheses than might otherwise be possible. So to explore for a first time of what is the SEM and what does it have to offer, I'm going to work through a hypothetical example, but it's actually drawn from my own work. When I started in grad school, I was interested in the intergenerational transmission of parental alcoholism on child behavior, particularly child drug and alcohol use. And so let's consider a single binary variable, and I'm going to call it COA. That stands for a child of an alcoholic. And so it can take on a value of 0 if the child does not have an alcoholic parent, and 1 if the child does have an alcoholic parent. And so in the project on which I worked is we did face-to-face interviews with the parents and got DSM diagnostic abuse or dependence status on the parents, and then we interviewed the child. All right, so then let's take as an outcome, say, adolescent substance use. All right, so this is some continuous measure of the child's drug and alcohol use. Now, that's not going to be normally distributed, but for now, let's just pretend it is. In a later episode, I'll talk about ways that we can do handle data that are not normally distributed. So what we have here is a very basic SEM. We have a single predictor, independent variable. We have a single outcome or a criterion or a dependent variable. Those all mean the same thing. Now notice, because this is a grouping variable, it's either 0 or 1. This is a continuous variable, so there's individual variability in adolescent substance use. This actually is a t-test. It's a 2-group t-test. But we can fit that as an SEM. So let's say that, just making up a number on a scale is we get some significant prediction of adolescent substance use from COA status. And what this would indicate is that the mean on adolescent substance use is half a unit higher for kids who had an alcoholic parent compared to kids who did not. So this is a simple, basic SEM that is a t-test, but we're capturing this in this predictor criterion relationship. So why on earth go to all the work to do an SEM when we can just use proc t-test or t-test or whatever it is in whatever program you would use? The reason is this is only the very first step in what we can use the model to build. So let's just make things up as we go along and see how these come up in things that we've seen before. Well, if we have a single predictor, so we have parental alcoholism diagnosis, all right, a question might arise, well, is it parental alcoholism diagnosis that's associated with elevated substance use, or is there some other comorbid or correlated predictor? So maybe we want to include ASPD, that's antisocial personality disorder. So that's comorbid with alcoholism, and we want to control for that. We could control for major affective disorder, depression, anxiety, things like that. But we could also control for things like parent education, all right? Or say socioeconomic status, anything we want, all right? And all of these we can use to predict the outcome, adolescent substance use. And these we will all correlate because that allows us to get the unique predictability. Dan has a great set of videos that really explore these issues within the multiple regression model. And so I'll defer you to watching that if you're interested in the details of this. But notice what we've done is now we're regressing a single outcome on a set of predictors, and we're controlling for all of these predictors and then evaluating parental alcoholism. So we might get, some non-significant predictor for major affective disorder, maybe ASPD is significant, whatever the details are. These are each coming out to be significant predictors. And maybe this value goes from 0.5 to say 0.3, but we determine that to still be a unique predictor of the outcome. Well, if you notice, this is actually a multiple regression model. We have a set of predictors. We can evaluate the entire set through a measure of multiple R squared, but we can also evaluate each unique predictor in the prediction of the outcome, all right? So that is also an SEM, so multiple regression is an SEM. But what else can we do here? Well, this is really interesting because is this the model that we're really interested from a substantive standpoint? What we're doing is we're trying to get an optimal linear combination of our set of predictors in predicting the outcome, right? Optimal meaning it's kind of the best with respect to some criterion, all right? And well, in regression, we use ordinary least squares. Again, see Dan's video on that for a really good explanation. But what's interesting is from my own standpoint, this model at this point is not terribly helpful to me. And it's not helpful for two reasons. One is it still doesn't explain why an adolescent who has an alcoholic parent is at an elevated risk for substance use, right? There's no mediating mechanism. There's no etiological mechanism. And so I don't have any intervening variables to say, well, the reason that an adolescent is at elevated risk is because in a home with an alcoholic parent, there is what? Well, we don't have anything there. Second point, and related to the first, is if we don't understand the etiological mechanism, then at least as a clinical psychologist, which is my original training, I don't know how to intervene into the system. So if I know that there's a child who has an alcoholic parent, if I don't understand the etiological or causal mechanism, I can't design an intervention program or a prevention program. All right, well, how does the SEM help us with that? Well, we can very easily, as we'll see in later episodes, we can expand this to say, all right, well, what if having an alcoholic parent increases stress in the home? Okay, and stress in the home is related to negative affect for the child, depression and anxiety. And negative affect is associated with increased adolescent substance use. Well, notice now we have a mediating mechanism. That's asking the why. Why is an adolescent at elevated risk if they have an alcoholic parent? Well, having an alcoholic parent increases uncontrollable life stressful events. Uncontrollable life stressful events is associated with greater negative affect, and negative affect is associated with greater substance use. Okay, so now we're a step closer in understanding the etiology of that process. All right, is that the only mechanism? Well, no. What about, say, parenting? All right. Is maybe having an alcoholic parent disrupts parenting, monitoring consistency of discipline, support, things like that, and that has an influence on adolescent substance use. All right, well, why there? Well, maybe peer influences. If you have decremented parenting, that increases delinquent peer associations, which then predict adolescent substance use. What about maybe some biological component? All right, we know that there's not a single gene that defines alcoholism, but there's increasing evidence that there are a lot of biologically based propensities to respond to the environment, right? That's temperament, that influence things like what are sometimes called now executive functioning, is frustration tolerance, planfulness, things like that. Maybe having an alcoholic parent increases high-risk temperament that then influences negative affect and moves on to the influence on substance use. I'm just making this up as I go along. These relations are real, they're drawn from the research, but I'm just putting them on as kind of on the fly. But what you can see is we've moved from that multiple regression model, which is just what is the optimal linear combination of the set of predictors and how does that maximize the multiple R squared in the outcome. And now we've started to move to a explanatory model. Not only might I be closer to understanding etiology of this process, right? What leads to what leads to what? But if I understand this, maybe I can say, all right, could I design a parent training program that would improve parenting in households that have an alcoholic parent? And if so, might that weaken the mediated effect of alcoholism to parenting to peer to substance use, and so on. And there are a whole variety of interventions that have been designed that are based on this premise. All right, so this is very, very difficult to estimate in a multiple regression model. In some ways it's possible, but functionally we can't do this model as we can in the SEM. So that's another huge advantage of the structural equation model. Now, what are some other things it could do? Well, in later videos, I will describe what a latent variable is. And so here, negative affect, notice it's just presented as a square, which means it's a manifest or measured variable. And say I did what we all usually do. If you have a 10-item scale, you add them up and divide by 10, and that's your score. Well, from classical test theory and psychometrics, we know that that's not the best way in all situations to get a measure. The SEM can allow us to estimate a latent factor, which I can draw as a circle, latent meaning unobserved, and I've got a whole later video that discusses this, that's defined by these multiple indicators, okay? So these are the individual items on the scale, and then what we're doing is we're trying to disaggregate the measurement error with each item with the so-called true underlying variance. And I use air quotes true because it's under certain assumptions and if our model is correct and our measurement is correct. But this is going to ultimately give us a better capturing of our underlying construct and a better estimate of the role that it plays in the etiological mechanism. So the SEM allows us to use multiple indicator latent factors in this way. All right, what else can it do? Well, we can do a multiple group model where we say, well, what does this path diagram, all right, or this etiological mechanism, how does it relate for boys and girls? Is there a significantly stronger stress to negative affect to substance use path for girls compared to boys? The SEM allows us to test that. As I've drawn this, this is all cross-sectional. All right, and as a field, we're really starting to try to move beyond that and to try to get repeated measures, is we could use the SEM to have time 1 substance use, time 2 substance use, time 3 substance use, and put a growth model on this end. All right, I've got a whole series of videos on growth modeling that we have on this channel as well. But instead of just predicting substance use in adolescents, we build a model to predict rates of change in substance use. So there are a whole variety of things that we can do with the SEM, and to varying degrees I'll explore these in later videos. So briefly, there are a series of steps that we need to consider in how we go about building an SEM, evaluating it, interpreting it with our own data. And I'm going to lay these steps out very briefly now. Ken Bollen, in his book, his structural equation modeling book from 1989, which is the gold standard, and I would highly recommend looking at that if you have the opportunity. It's rigorous, it's technical in parts, but it's also very accessible, and it's kind of the gold standard in structural equation modeling. But Ken lays out these series of steps, and I'm going to frame the videos and the office hour episodes that come up around this. So the first one is called specification. All right, so this is literally, how do we draw the model? Now that's a colloquialism, right? The drawing the model is actually laying out what are the equations, what do we believe the independent variables are, the dependent variables, the mediators, the moderators, what are latent factors, what are what are manifest variables. So the specification is what variables do you have in your data set, and how are you going to relate those to one another? Are you going to have COA predict stress, predict negative affect, predict substance use? Or are you going to have COA predict stress, but stress jointly predicts negative affect and substance use? Those are different specifications. And so in later videos, we'll talk a lot about that. How do you identify what the specification is? How do you do that that's in a way that's close to theory, all right, and what your research hypotheses are? Once you've specified the model, then we have to do something that's very tricky and quite honestly is not done in practice as much as it probably should be, which is identification. All right, and I'll touch on this in a later video, but not in a lot of detail because it's a broad topic and it gets pretty complicated pretty quickly. But from a broad standpoint, identification is, did you have enough observed information in your data? So we have means and variances and covariances. Do you have enough information to estimate the parameters that you want to in your model? And so it's kind of having dollars in the bank, is you need more pieces of information, or at least the same amount, but we aspire to more pieces of information that you observed in your sample than the number of parameters that we're going to estimate. And so there are ways of doing model identification. All right, so we'll talk about that. The third step is very important. It's called estimation. All right, so notice we've defined our model. We've established we have enough information to estimate the pieces that we want. And now we're going to estimate sample parameters based upon the characteristic of our data. Well, when I came up through the ranks a long time ago, is really there was just maximum likelihood. There was just normal theory maximum likelihood. And so we would evaluate this step, but it was kind of the only game in town. That is not the case anymore. We have a whole variety of estimators from which we can choose that are normal theory maximum likelihood, robust maximum likelihood, weighted least squares, asymptotic distribution free. We have two-stage least squares. There are a whole variety of ways that we can obtain parameter estimates from our data, and we need to make a knowledgeable decision about that. And I'll talk about that as the videos proceed. All right, so we estimate, and then the fourth step is arguably the most interesting, at least from a methodological standpoint, and that is evaluation. All right, is how do we determine if the model fits good enough? And what we're going to find, first, there's like a century of work on this, and especially the last 20, 25 years has been a lot of contributions and exploration in this. And Dan and I have contributed to this literature in various ways. But this is literally, you fit a model, you obtain your estimates back. Is it a good fit? Is it appropriate? Can you draw inferences from your data that you have some confidence in? Or is there a misfit in the data that you need to address and evaluate? And my own opinion is there's never going to be some consensus that if your fit index is greater than this and your p-value is less than this, then your model is correct. It's just simply too complex, too multifaceted, and we need to use our brain more. We need to think about theory and replication and reproducibility and things like that. So we'll talk about that. Based on 4, all right, now we get into even kind of more controversial topic, which is respecification. All right, so let's say in step number 4, we decide, no, the model doesn't fit well. The model, that the parameterization, notice how these all link together. How I linked my variables that I observed and have, how I put those together does not adequately reproduce the characteristics of the data I saw. It just doesn't fit well. So what do? Well, you can either lock up and go home, but that's not completely satisfying. And so there are a whole lot of ways that we can say, well, if my hypothesized model didn't fit well, what do the data suggest I do to modify the model? So we can make respecifications that are based on theory. We can say, oh, well, you know what, is maybe we need these 3 parameters that weren't in the original model because this theory says that. And that's good. We can test competing models, and we can use a thing called likelihood ratio test to compare. And actually, I think that's one of the real strengths of the SEM, and as a field, we should do that more. But there are also these wonderful little things, and they're wonderful in the sense that they're very cool analytically, but they are also very dangerous to use, which is I'm actually getting a cell phone call, which I'm going to decline. Sorry about that. If I were a student in my class, I would yell at me right now. So we have these wonderful little things called modification indices or Lagrange multipliers. They're the same thing. And what they do, they're totally analytically based. They're actually functions of derivatives. And the model tells you if you free this parameter, your model will be improved by this much. All right, and we'll talk about these in later videos. They're very dangerous to use, but they can also help us think about that path model I drew, is if we have 1 or 2 omitted pathways that really want to be there, the data can speak to us in ways that we could include those. But that's a data-driven decision that's not a priori and hypothesis and theory-driven, and are very, very dangerous to do. So we can talk about that later. And then when we establish a final model, then we have interpretation, all right? And that is just how do we communicate our findings to a broader audience in some meaningful way. And so we have a hypothetico-deductive process of science, is we have theory, we narrow it down to research hypotheses, we test them, and then we make generalizations. This is very tricky, we are going to be tempted, I think, to sometimes interpret the results beyond what the data allow. I have read a lot of discussion sections, I've written some discussion sections that make inferences that move beyond what the numerical results support. And so we have to be very careful about that. So in the videos that are to come, I am gonna evaluate or discuss different parts of these steps in different ways. And what we're going to do is talk about a little bit more about regression as a structural equation model and introduce path diagrammings and things like that. We're going to expand it and talk about path analysis, where we have mediated mechanisms. How do we test mediation? How do we test moderation? I'll talk about what is a latent variable, what are the advantages, how do we incorporate that into the model, and then expand it to a full SEM where we have multiple indicator latent factors, where we have some predicting others, we have mediation, we have moderation as well. And then we can move into some really interesting topics, is what do we do with SEMs if we have discrete outcomes? So binary outcomes or counts or non-normally distributed data. And what do we do if we have longitudinal data? This is a really powerful approach with the SEM, and I have a whole series of videos on that in growth modeling if you're interested in learning more details about that. So in a nutshell, this is a general introduction to the SEM, and in the following videos I'm going to pick away at different parts of this with the realization that I can only skim across the surface. Here at University of North Carolina, we have an SEM class, so a 16-week doctoral level, and we have an advanced SEM class, and that's another 16 weeks. And so these videos can only kind of skip along the surface, but knowing that when you find something that might be of interest to you, then you can drill down more when you get there. So that's an overall intro. I hope this is of interest to you. And as always, thank you for your time.